Hey guys, welcome to your review on sensation and perception. My daughter is currently in ballet, so I am recording this in my car. If everything sounds a little bit funny, that's why. All right, so let's get started. All right, guys, so sensation and perception. Sensation is going to be any of the information that we're bringing into our brain through our eyes, our ears, our skin, whatever, but any of your sensory organs bringing in information. And sensation is the raw information. Now, perception is the understanding that we make from those sensations. So a perception could be things like color constancy laws, size constancy. It can be anything that we exploit with visual illusions. All of those kind of shortcuts and rules to our environment, things that make things predictable. That's how we perceive it. You should know the difference between bottom-up and top-down processing. Bottom-up processing, going from basic sensory information into a larger precept. Top-down processing, you're going from an already existing or pre-existing idea into applying it to a scenario. So bottom-up processing, you try a brand new food that you've never tried before and you notice the texture and the taste and the smell. Top-down processing, I'm handing you something you've eaten before, and even before you put it in your mouth, you have an assumption of what it would taste like. Absolute threshold, the minimum amount of stimulation that you need 50% of the time to detect a stimulus. Now, that's the basic definition. The car example that I always seem to use for you guys is the idea that you're sitting in the car, and at what point would someone have to turn the volume up on your radio for you to notice it? Now, remember, this is going to be the first time that you notice it consistently 50% of the time. If I was sitting in the car with my mom has worse hearing than I do. Her absolute threshold would be higher than mine. She needs more stimulation than I do to detect sound. Signal detection theory says that maybe there is no single absolute minimum threshold, that maybe our thresholds are impacted by other factors. Factors like how alert you are, how awake you are, whether you're expecting that stimulus, whether you even care to detect the stimulus. So it's not that there is a single absolute, but there are multiple factors that actually determine whether or not you detect an absolute. Signal detection theory will be on the AP exam. They hit it almost every year. Please study this one. So I always give you guys the example of, I don't know, Billy who's playing his drums, and when he plays his drums, he normally doesn't hear the phone. Then one day he's waiting for a record contract and he's playing the drums and he hears the phone that day. Well, because Billy actually cared that day and he was being more attentive, he heard it. His absolute threshold was more sensitive on that day due to an outside factor. Just noticeable difference, different threshold, or the J and D. Now, this is going to be whether or not you can detect a change. So we would say that change is constant, and that's Weber's law. Now, Weber's law has a different constancy for light, for sound, for touch, or pressure and weight. Easiest way to remember this one. For you to determine a change, the change has to be relative to what the kind of starting situation was. So for me to notice a change between a really silent situation and hearing a pin drop, and then actually hearing an increase in volume in a crowded auditorium, the crowded auditorium, it has to be louder than a pin drop for me to hear the change, to notice that a change has occurred. It needs to be something exponentially larger. So Weber's law says that for us to detect a change, it has to be constant. Just noticeable difference, the amount of change required between one stimuli and another to detect that a change has occurred 50% of the time. And remember, 50% means above chance. Okay, the concept of priming will come up in other areas, but priming literally is being given exposure to something to anticipate it in the future. So sometimes we're more sensitive to a stimulus or to an event if we have the anticipation of the event coming. Sensory adaptation. Remember, to adapt to something is to get used to it. So when you adapt your senses, they stop paying attention to the things that are consistently there. The humming of the projector in the classroom is a sensory adaptation. You don't pay attention to it because it never leaves. It is always humming. So stop paying attention to it. I always use the example of how many of you guys have thought about your underwear today. Weird, I know, but still, if you haven't thought about your underwear today, it's because it's always, I hope, always there. And therefore, there's no need to pay attention to it. Selective attention. This is that in almost any case, we can only attend to a very few number of things in our environment. So we select what we attend to. And obviously, we attend to what we think is the most important thing. Now, the cocktail party effect deals with usually what we'd consider late selective attention. In other words, you are already primed. You have an expectation of responding to things like your name. So if I hear Jess, even if it is in a very crowded situation where there could be several other people named Jessica, I still will, while having a conversation with somebody else and paying attention to them, in the midst of my conversation, if I hear my name, it will pull my attention away and I'll pay attention to something else. And just like all of that, I can only really pay attention to either the conversation that I'm having or my name being called off and my attention being pulled away and me paying attention to my name. So we can only truly pay attention to one single thing. Transduction. This is going to be the change of a sensory stimulus, usually something like a light energy or a sound energy, being converted into a neurochemical message that can be read by the neurons and the brain. And so we'll look at phototransduction and acoustic transduction. So right now we're really into talking about the sensation part of this unit. So amplitude and frequency of waves. We've talked about this. Now remember, light waves are actually measured in their length. So I can already tell you the longest light wave is going to be red because it's the very top arc of a rainbow. You flatten out a rainbow, red is longer than purple. Red is a longer wavelength. It's somewhere around the 900 nanometers range, where purple is somewhere around the 470 range. So 470 nanometers is shorter than about 900 nanometers. Now, that's going to be the wavelength. Wavelength will help us with hue or color. Amplitude, however, is going to be the height of the wave, and it tells us how bright or how loud a color is. So 900 nanometers and a really kind of high amplitude of the wave means that it's a bright, bright red. 900 nanometers but a very short wave means that it's red, but it's probably a duller red. Now, you should know all the different parts of the eye. Make sure that you understand that light waves first come through the cornea, which is that clear protective structure that protects the rest of the eye. It then goes through the pupil, which is basically a hole that is created by the iris, which is a colored band of muscles. It then gets further focused by the lens that does accommodation. So here's accommodation. The lens actually changes its shape. It accommodates itself to focus the image on the best part of the retina. So the lens is the part that accommodates. It actually changes its shape. On the retina, you have your photoreceptor cells, which are going to be your rods and your cones. Then you have your bipolar cells, your ganglion cells. The axon ends of the ganglion cells form the optic nerve. The optic nerve exits out at the blind spot, which is called such because there are no photoreceptor cells, and the photoreceptor cells are the cells that do phototransduction. So they turn the light wave into a chemical message that then the bipolar and the ganglion cells can read. It exits out the optic nerve through the blind spot, crosses over at the optic chiasm, goes to the thalamus, the one part of your brain that tells it that it is a visual signal, and then it should eventually end up in the occipital lobe where feature detector cells try to put the image back together. If that was a giant blur, just rewind this and listen to it again. I'm sure I have some other stuff to talk a little bit more in depth about rods and cones. Theories of color vision. You should know the trichromatic theory. Trichromatic, 3 chroma, 3 colors. That means that you have a red cone, a blue cone, and a green cone. And let me put it in the right order. Red for long wavelength, green for medium wavelength, and blue for short wavelength. And how do you know that's how they go? It's because that's the order they are in a rainbow. So right back to rainbows. Trichromatic theory says that we have these 3 cones, and through these 3 cones, a very different amount of stimulation of each of the cones gives us the full spectrum of every color we have ever seen. So if you're looking at something that is yellow, you are firing both red cones and green cones simultaneously to let you see that kind of averaged color between the two of yellows and oranges. Opponent processing theory. Opponent processing theory has to do with after images. If I stare at something white for a long time, I see its after image of black. If I stare at something yellow for a long time, I've stimulated both my red and my green photoreceptors. I have left my blue photoreceptor alone. So when those two get fatigued, my blue photoreceptor comes on. So I stare at yellow, I'll see blue. If I stare at blue, red and green have been suppressed, and so then all of a sudden I'll see yellow. So blue and yellow go together. They're the after images of each other. And then red is going to be the opposition for green. So if I stare at red for too long, then I will see green when I look away, and if I stare at green too long, I'll see red when I look away. Your feature detector neurons are the cells in the back of the brain that put the message back together. So think of the fact that as you're taking in color and shape and form and motion, these are all different bits and pieces to a puzzle, and you need to put the puzzle back together. Feature detector neurons in the back of your brain, in your occipital lobe, are going to be the things that detect and understand what those messages are and then puts them back together. They do this in a form called parallel processing. In other words, you don't see motion and then color and then shape. You see it all at the same time. So we do have a momentary delay in what we perceive versus what's going on in the world. And it's about 1/3 of a second delay because our brain needs to compute it all and put it all together. It puts everything together at the same time. So they process it in parallel. Then we have light versus dark adaptation. How quickly do you adapt to a light environment versus how quickly do you adapt to a dark environment? Light environment, we adapt very quickly. Our cones are very color and light sensitive. So when we have a strong light source, our cones kick on really quick and we like the light. We are diurnal. We like to be around when it's bright out. If we're looking at dark adaptation, would you want to run into a dark room? The answer is no. It takes longer for our rods, which are going to be the kind of motion and grayscale photoreceptors, for them to activate. And so they need low light conditions, but they're not going to be as quick to respond as our cones are. And remember, you have that fovea, that area of highest concentration and best vision, that is fully packed with nothing but cones. Lateral antagonism is what allows us to see contours. So this is the idea that when there is a change visually, we have cells that are firing and cells that are suppressing, and that lets us register the difference between those two patterns, and therefore you will see a contour. You'll see a change in color, a change in pattern, a change, but that's what comes from lateral antagonism. So in other words, we annoy the thing next to us so we can tell a difference. All right, on to sound. Amplitude and frequency again. Sound waves, the length of the wave matters. So if something is shrill or high pitched, you are looking at a short wave. If it is a longer wave, it's usually a deeper sound. Now, when we talk about the amplitude of the wave, not the length of the wave, but the amplitude, how tall it is. Something that's loud, high amplitude. Something's very quiet, very short amplitude. So the shorter in height the wave, the quieter it is. The shorter in length of the wave, the shriller it is. The taller in height of a wave, the louder it is. And the longer in length of the wave, the deeper the sound is. You should know all parts of the ear. Make sure that you know that it goes from pinna to auditory canal to tympanic membrane to the ossicles to the oval window. Once I say cochlea, that is the structure that does acoustic transduction. That is the area that carries the basilar membrane and the hair cells. The hair cells are going to be the cells that do acoustic transduction. So basilar membrane, hair cells, they move back and forth. When the wave within the cochlea moves them back and forth, that then generates a neural impulse, which then travels out the auditory canal, that then goes to the thalamus and then to the temporal lobe. Localization of sound is going to be different than place theory. And so please make sure that you know the difference in these two. Place theory is not a location in a room. That's localization of sound. Place theory literally is the specific place on the basilar membrane is going to be stimulated and therefore you hear sound or a specific pitch. Frequency theory is the entire idea that the entire basilar membrane vibrates together as one, and the rate of vibration then determines the pitch that you hear. And what we know is that they're both a little bit correct. The basilar membrane doesn't vibrate quick enough to hit a lot of the high pitches, and the different areas, the deeper you go into the ear versus the more exterior of the ear, they will process different pitch. Make sure you know the difference between place and frequency. Place, location on the basilar membrane. Frequency, the entire basilar membrane will actually vibrate. Localization of sound, your head is a giant shadow for your two ears. It's an orb that's stuck in between the two. And so there is a time delay between your left ear and your right ear. And there's an intensity delay between your left ear and your right ear. And so if you're hearing something off to the left side of your body, it was louder and faster in your left ear than it was in your right. That allows you to localize where in space that occurred. Now we're moving on to pain. The only real theory that you need to know for pain is the gate control theory. And that basically is that your spinal column works like a large gate system. Large neural fibers allow messages to block the sending of something like a pain message. Small neural fibers allow the messages to continue through. And again, I like to use the idea that if you rolled a boulder in front of a gate, it would stop a message. So if you have a large neural fiber being excited, it prevents the small pain fibers from sending their messages. It essentially blocks them. Small pain fibers, they are like little pebbles. You can usually scoot them through or underneath a gate so they can sneak their way in. That means that for someone who is processing pain, the pain message goes to the brain makes the determination about whether or not they can actually deal with that pain message, and then it will activate the spinal column to either stop the message with a large neural fiber or allow the message to continue through with smaller neural fibers. All right, for touch, know your sensations of touch. You have warm, cold, pressure, and pain. Pressure has the only identifiable unique cells for that sensation. For taste and smell, they're both chemical senses, and they're called chemical senses because they detect chemicals in our environment. You guys should remember that from midterm. It really is just that simple. Anosmia is the inability to smell. Pheromones, those are going to be chemicals that humans and animals put out that actually attract others based off of sense of smell. We don't really use them because that would just be gross. Synesthesia is cross-wiring of senses. In other words, you may have somebody who, when they hear a number, they visually in their visual field see a color. They have different sounds associated with different letters, et cetera, et cetera. But basically that their sensory modalities are cross-wired, and the idea is that this is probably happening somewhere at the thalamus. Your vestibular sense and your kinesthetic sense. All right, your kinesthetic sense is also known as proprioception. It is your ability to know where your body parts are in space without having to look at them. It is controlled by your cerebellum. This is going to be your ability to understand where your ankles are, your wrists are, without even looking at them. You can detect them and you could point to them. It's what also helps you deal with things like balance, walking heel to toe, something like that. Your vestibular sense has to do with literally finding your horizon line. So this one, truly more than kinesthetic, is your absolute balance. This is what allows you to determine up from down, and really kind of the idea of spinning around and maintaining a horizon point. So your kinesthetic sense lets you know where your body parts are in space. You can walk a straight line without having to look down. Your vestibular sense allows you to maintain your balance, know where your horizon is, know up from down. All right, so these should be fairly familiar to you. If you can't remember how transduction goes, whether you're talking about visual transduction or acoustic transduction, this is one of those times that you do need to come see me. Really, the big things are knowing structures, knowing what they do, and then being certain what the transduction structures are. So in the eye, the retina, and the cells, the photoreceptor cells, the rods and the cones, and in the ear, the cochlea, but specifically the hair cells of the cochlea. Now we're on to the last little bit of perception. And remember, with perception, we talked about a lot of kind of interesting things like monocular depth cues, binocular depth cues, constancy rules, etc., etc. So monocular depth cues, make sure that you remember things like interposition. When one thing is in front of something else and I'm looking at it with a single eye, I can tell the thing that is closer to me is closer because it is blocking what is behind it. I know that sounds kind of very commonsensical, but that's interposition. Relative size and relative height, a lot of you guys had some issues with. Relative size, objects that are closer to me appear to be larger in size. Things that are further away, if they are known size, they still seem smaller. So a tree that is close to me will look much larger to me than a tree that is far away, even though I can assume that the trees are roughly the same size tree. Brightness, objects that closer to me appear to be bathed in more light. Texture, objects that are close to me appear to have more gross or large, coarse texture to them. When they're further away, the texture seems to be more fine or harder to detect. Relative height, another problem one. Objects that are further away from me appear to be higher in my field of vision. In other words, they're not taller than me. That's not what we're talking about. They just appear to rise up or be higher in my field of vision. Look at anything that's far away from you and figure out where the bottom is. Now look at something close to you and figure out where the bottom is. The thing that's closer to you is going to be lower visually, especially if you're only using one eye, because these are monocular, remember, single eye. Linear perspective, objects converge, parallel lines will converge in a distance. Now, you may want to remember things like the Mueller-Lyer illusion. That will help you with some of this. You may want to also go over and look at the Ponzo illusion. Those will also kind of help. Binocular cues. There's only two, convergence and retinal disparity. Convergence is not the same as linear perspective. Convergence in this case is talking about your eyes going cross-eyed. So your eyes converge. You need two for a binocular cue. So this allows us to perceive motion. As things get closer, our eyes start to turn inwards. As things move further away and at 25 feet, they basically go straight ahead. Retinal disparity, you have two retinas and they disagree with what they're seeing, and so the overlap of those two different pictures gives you 3 dimension. It's like using a viewfinder. Then we have the grouping principles for Gestalt. Remember the law of Prägnanz, law of simplicity. We like to group things as simple as possible. So figure ground, what you pay attention to is the figure, everything else is the background. Closure. We like to visually close off objects. We use subjective contours. So we like to draw in the lines when the lines don't exist. Similarity. When given the option, I will group things that look alike together. Proximity. When given the option, I may just group things that are closer to each other together. Continuity. I perceive things as being continuous as opposed to seeing things as broken or oddly, changing direction type lines. And connectedness. If things are touching, I'm more likely to group them together because of that fact. With motion perception, you need to know stroboscopic effect and then the Phi phenomenon. And remember, the Phi phenomenon is the one that seems to have the strobe light and stroboscopic doesn't. So, Phi phenomenon first. The Phi phenomenon with the alternating turning on and off of lights, you perceive motion. In other words, this is going to be like a V dot sign. You seem to think that the dots are moving around the sign, or in the amazing dancing lights illusion that I showed you guys before in class, you seem to think that that light or the dots are moving around in a circle, and it's not. It's the turning on and off of lights. Stroboscopic effect, that is a flip book. So the very quick and alternating images that are static allow you to perceive motion. Cartoons are this, movies are this. It's basically a flip book. Change blindness, before I get ahead. Change blindness, inability to detect change. Usually this is due to the fact that we can only focus on so many things, and when things that happen that are going to be unexpected and we are not paying attention to, we don't see them anyway. So we are going to be blind due to the fact that we can only fixate on certain things. The more attention getting something is, the more likely we are to experience change blindness. And the Stroop task. The Stroop task deals with your ability to cognitively deal with competing things. And so this is where you have something that's written in one color, but it is a word that is not that color. So you have the word blue written in red ink, and you have the word green written in blue ink. If you were to read the word, we almost automatically process that. You will read it perfectly fine, but when you are asked to say the color and not read the word, you will have about a quarter of a second cognitive delay, because you will fall back on your kind of primed or automatic ability to read. The constancies you guys should know. Shape constancy. We perceive things to stay the same shape and that they don't morph. So that door that you just shut went from a rectangle to a rectangle and stayed a rectangle, even though truly it probably went to a trapezoid, to a much thinner trapezoid, to maybe even possibly a rectangle at one point. Color constancy, we already talked about that earlier in this. Despite illumination, we perceive color to be the same. And size constancy. I don't think that you've gotten taller as you've walked closer to me in the hallway. I know that your size stays constant, that's just an indication of motion. Perceptual sets. These are going to be ready ways to perceive things in our environment. We have kind of this set assumption for certain things, a way that we choose to perceive them. And then perceptual adaptation. Once we get used to something, we no longer really pay attention to it. It's like sensory adaptation. If you get used to perceiving something a certain way, you may not really pay attention to it anymore. You adapt to it. All right, guys, so that's all I really have for this. There might be more in here that I didn't cover, but if you have any questions, this is one of those times that you need to come and let me know. Like I said, I'm going to try to keep these all to about 25 minutes as best I can. See me in class if you have any questions about sensation and perception.